Welcome back. In this video, we're going to verify that the difference of these vectors, u minus the projection of u onto v, is orthogonal or perpendicular to the projection of u onto v. So here we have vector u in blue and vector v in black, and the projection occurs when we drop that 90 or that perpendicular down to vector v. So this red vector represents the projection of u onto v. We are wanting to show that the difference of u minus that projection is perpendicular or orthogonal. All right, and so really this is very similar to our parallelogram law when we think about adding and subtracting vectors. So what we're going to do, the vector projection of u onto v, well, we know that's always going to be parallel to v. So we'll say the projection of u onto v, which we know is given by u dot v over the magnitude of v squared times the vector v, we know that's going to be parallel to v. At this point then, we can presume that u minus the projection of u onto v is orthogonal. So in order to do this, if we need to verify that they're orthogonal, right, we're going to verify, we want to show that they're orthogonal, then what do we need to show? Well, we know that the dot product of orthogonal vectors, we want to show that cannot write today, that the dot product equals 0. So if we want to show these two vectors are orthogonal, we need to show that u minus the projection of u onto v dot v is equal to 0. We want to show this is equal to 0. So what I'm going to do, I'm not going to say that it's just equal to 0. I can't do that. I have to prove that, which means I need to manipulate this into a manner that as I perform my calculations, it turns into 0. So let's think about what is the projection of u onto v? How would we calculate that? So this is the same as u minus the projection of u onto v is u dot v over the magnitude of v squared times v. So we have this dot v. Now we know that we can distribute dealing with dot products. So this is u dot v minus u dot v over the magnitude of v squared times v, and we can say dot v. So technically we have this dotted with v, but by property 2 of our dot product properties, I can say u dot v minus, I'm going to rewrite this, u dot v over the magnitude of v squared, and that would be times v dot v. Now, one thing we also know by property 4 is that v dot v is equal to the magnitude of v squared. And if we have them on the top and the bottom, they cancel to 1. So this leaves me with u dot v minus u dot v. And of course, anything minus itself is equal to 0. Therefore, we've proven algebraically, we've manipulated u minus the projection of u onto v, dotted with v, and shown that those two are equal to 0. And that dot product being equal to 0 means that those two vectors are orthogonal. We have one more example to do in this video. We're going to talk a little bit about work. So for our last part of the discussion in this section, we're going to talk about work. Work, as we previously discussed in Calculus 2, can be calculated by saying W equals FD. Work done by a constant force of magnitude F in moving an object through a distance D can be defined this way. But that formula holds only if the force is directed along the line of motion. So we're moving something and the force is directed along that line of motion. But if the force F moving an object through the displacement D has some other direction, we have a different way we need to think about it. Let me pull in a visual. So here we have some object that we moved from point P to Q. And if a force is moving an object, the force is pushing in a different direction than that actual motion. We say that the force F moving the object through the displacement D, represented by the vector PQ, has some other direction than the work performed by the component of F in the direction of D is given by this F cosine theta times the D, which ends up being represented as the dot product of F dot D. So I'm going to write that out. We have work. So we have a scalar component of F in the direction of the vector D. So D is a vector and this force is a vector. I'm trying to make them look a little bold. So we have that times the length of vector D. So that scalar is calculated by the magnitude of vector F times cosine of that angle theta. I'm not going to put a dot there, but times then the magnitude of vector D, which simplifies to vector F dot vector D. So work, instead of being force times direction, it's going to be the force vector dot the displacement vector or the direction vector. So more formally or written a little bit nicer, the work done by a constant force acting through a displacement D, which is that vector PQ in our diagram up above, that work is the dot product of the force vector dot the displacement vector. Let's do one example. So for example, if we have some magnitude for our force vector at 40 newtons, and D, the magnitude of my displacement vector, is 3 meters. And we know that the angle theta was 60 degrees. And if we wanted to find the work done by the force F in acting from P to Q, in that movement across that 3 meter distance, then the work is F dot D, or rather the magnitude of F times the magnitude of D times the cosine of theta. So my force is 40, my displacement vector is 3, and then we have times the cosine of 60 degrees, which is 120. 40 times 3, cosine of 60 is 1/2. Multiplying that, we get an output of 60. and we measure work in joules, Joules. So as we move forward and we get to chapter 16, we will encounter more challenging work problems. And when we're dealing with that, we're going to be dealing with work done by a variable force along a general path in space. All right. So that concludes our lecture for this section. We have 5 videos in total. As always, email me if you have any questions.